Space as a measurement of length or volume here on our gorgeous blue planet is fairly easy to understand. A 30cm ruler, a 400-gram tin can, or a 500ml bottle of Pepsi are all things that you can picture and probably estimate accurately. But located in the constellation of Canes Venezia is a spherical and literal void of nothing. Though not officially classed as the largest void found, the giant void just so happens to be a neighbour of the current number 1 spot, named Butte's Void. Approximately 1.5 billion light-years away, the sheer size of this void is as close in size as it is in distance if it were to be measured from here on Earth to its residential constellation in the northern galactic hemisphere. Discovered in 1988 by Alexander Kopolov at the Special Astrophysical Observatory in Russia, the giant void currently retains its place as the second largest void of this kind ever detected. Despite what the name suggests and its unimaginable vastness, the giant void isn't completely alone. Astronomers have found that there are approximately 17 galaxy clusters hidden inside. In a concentrated spherical neighborhood, studies of the motion of the clusters show that the galaxies have no interaction with each other whatsoever, meaning that the density of the clusters is very low, resulting in a weak gravitational pull. Very little is known why there are these massive areas of nothing, or how they came to be this way, but it does make for interesting theories and imaginative thought down here on Earth. Barnard 68 is a molecular cloud, also referred to as a dark absorption nebula. Well within our own galaxy and existing in the southern constellation of Ophiuchus, Barnard 68 is approximated to be in the region of 400 light-years away, and so close that not a single star can be seen between it and the Sun. Discovered by American astronomer Edward Emerson Barnard in 1919, Barnard was cataloguing a series of dark nebulae, and by the time he had published his findings in 1927, had come across 370 dark objects visible to a telescope and making micrometer measurements of planets, globular clusters, and planetary nebulae. This was done by using long-time exposure, a technique which, although still used today, is a subdiscipline in amateur astronomy for those seeking aesthetically beautiful images rather than scientific data. Barnard 68 is colder than cold, and because of its opacity, its interior temperature is estimated to be all the way down to minus 257 Celsius or minus 431 Fahrenheit. The nebula's overall mass is in the region of twice that of our Sun and measuring about half a light-year across. Despite being opaque at visible light wavelengths, use of the Very Large Telescope at the European Southern Observatory in the Atacama Desert of northern Chile, astronomers have discovered that this strange mass blocks out somewhere in the region of 3,700 stars on the opposite side. Observations obtained by the Herschel Space Observatory team were able to constrain the distribution of the dust component and its temperature even more. Having a dark cloud in the solar neighborhood greatly facilitates observation and measurement. If undisrupted by external forces, the stability of the cloud dust is a fine balance between outward pressure caused by heat or pressure of the cloud's contents and the inward gravitational forces generated by the same particles. This in turn causes the cloud to wobble or oscillate in a manner similar to a large soap bubble. And more interestingly still, Barnard 68 holds the very real potential to create and become a star. Gravity must gain the upper hand for a sustained period to cause the cloud to collapse in on itself. Reaching the right temperature and density, fusion, the reaction in which two or more atomic nuclei are combined, can take place. When this happens, the much smaller size of the star's envelope signals a new balance between greatly increased gravity and radiation pressure. For Barnard 68, gravitational collapse is inevitable, but it's going to take up to 200,000 years before we'll be able to see the end result. The cloud mass is estimated to be twice that of our Sun, with a width of about half a light year across, or if you will, 2.9 trillion miles. For context, the equator of our lovely planet is just under a humble 25,000 miles measured around, making the measurement of half a light year difficult to picture as a unit of length. But thanks to technology here on Earth, we can definitely get a gist of just how big this black cloud in the constellation of Ophiuchus is. Voids are more commonplace in the universe than previously thought. Vast expanses of empty space accountable for 80% of the observable universe. These empty regions can measure in the hundreds of millions of light years across. Just nothing in what would feel like forever. And it would be, even if humans could travel at light speed. According to researchers at the University of Wisconsin-Madison, our Milky Way could be floating at the near center of one of these voids. Using data from large-scale telescope surveys that count galaxies, the research has pointed to our own galaxy being in the center region of one of these voids. What's more surprising is that the estimation radius of the expanse we call home is in the area of 1 billion light years. If correct, our human species is living in the largest known void of the observable universe. Researchers first speculated the idea in 2013, but advanced the concept in early June 2017 in an effort to measure how rapidly the universe is expanding. The universe has been expanding since its existence began with the Big Bang, more than 13 billion years ago, with evidence suggesting the rate of expansion is in fact accelerating. Unfortunately, or perhaps fortunately, as we live in a relatively quiet neighborhood with threats that are few and very far between, cosmically speaking, the idea that we are the center stage of a void isn't unreasonable. But right now, there's no way to zoom out far enough to pinpoint the Milky Way spot in the wider universe. According to the experts, mathematically it's unlikely, but unlikely isn't impossible, and much less unfathomable. Scientists are hoping to make use of the void's distribution to explore the nature of dark energy, the unknown force responsible for accelerating the cosmos expansion. The possibility for studying dark energy and perhaps dark matter could also be made easier in these beyond massive dark territories of space. In 1987, astronomer David Jewett, who was then at the Massachusetts Institute of Technology, became increasingly puzzled by the apparent emptiness of our outer solar system, encouraging a then graduate student, Jane Liu, to aid in his search to look for something, anything, beyond Pluto's orbit. So using telescopes at the Kitt Peak National Observatory in Arizona and the Cerro Tololo Inter-American Observatory in Chile, Jewett and Liu set their gaze on what could be seen past our recently demoted dwarf planet. In 1988, the duo moved to the University of Hawaii to use the telescope at Mauna Kea. With an upgrade to the pixel imagery available, the telescope eventually gave them the results they had spent 5 years looking for. On Sunday 30th of August 1992, Jewett and Liu announced the discovery of the candidate Kuiper Belt project. To date, over 2,000 objects have been found to be circulating our outer solar system. But it's widely accepted that this hasn't even made a dent in what is left to be discovered, as astronomers estimate the belt region to be no less than 60 miles wide. Astronomers suggest that the icy objects that make up the Kuiper Belt are in fact remnants from the formation of our solar system, and if it wasn't for Neptune's continual presence through its orbital path passing through the Kuiper Belt, these smaller cold fragments would likely coalesce into a large planet. The amount of Kuiper Belt objects, or KBOs, is likely less than what was originally left over from our solar system's initial creation. Today, the Kuiper Belt is slowly eroding itself away, between collisions with other objects breaking each other into smaller fragments to being knocked out of the belt entirely, and solar winds. The total mass of all the material within the Kuiper Belt is thought to amount to around 10% of what we have here on Earth. A fairly large quantity of KBOs have either moons or binary objects, an object which is similar in size or mass that orbits around a point that lies between the two. Pluto, being the most well-known resident of the Kuiper Belt, has 5 moons currently accounted for within its orbit. There's a lot going on within the asteroid belt, and as much as we know about it, astronomers are only just getting started to document them. Defined as a hypothetical region of space-time and singularity that cannot be entered from the outside, a white hole does the opposite of a black hole. Instead of drawing in the space and objects around it, like that of its counterpart, white holes emit energy matter, light, and information. Like black holes, white holes have properties like mass, charge, and angular movements. They attract matter like any other mass, but objects falling towards a white hole would never actually reach the white hole's event horizon. In the case of the maximally extended Schwarzschild solution, a coordinate system for the Schwarzschild geometry for a black hole indicates that, in theory, the white hole's event horizon in the past becomes a black hole event horizon in the future. So any object falling towards it will eventually reach the black hole horizon. Acceleration due to gravity is greatest on the surface of any body, but since black holes lack a surface, acceleration due to gravity increases exponentially, but never reaches a final value, as there is no surface to a black or white hole, physically speaking. The concept for the existence of white holes was put forward by Russian cosmologist Igor Novikov in 1964. Predicted as a solution to the Einstein field equations, relating to the geometry of space-time to the distribution of the matter within it. If everything works as theorized, objects inside a white hole can leave and interact with the outside of it. But since nothing can enter a white hole, the interior is cut off from the past. Simply put, that no outside event will ever affect the inside. And yet, while general relativity describes white holes in a mathematical equation, there is very little in these theories about how they would form. A black hole cordons off its bit in space when a star collapses into a minute volume, but the process in reverse doesn't make physical sense. Not unlike an egg unscrambling itself, a violation of the statistical law, which insists that the universe becomes messier and more chaotic over time. It seems that in order for something like a black hole to exist, both in space and as an equation that follows the general relativity law, there has to also be an opposite which doesn't obey the rules. Or maybe we can't see it because the universe is the aftermath of a white hole. According to black hole physicists, the Big Bang explosion of matter and energy looks like potential white hole behavior. Hal Haggard of theoretical physics at Bars College in New York said that the geometry is very similar in the two cases, even to a point of being mathematically identical at times. There's still a lot we don't know about the nature of white and black holes alike, but it's a true testament to all the amazing work put in by these fantastic minds to enable us to look up in wonder and a little pinch of fear.